Noise, a potential hazard by which a submarine may give away its location to the enemy. Noise, one means of locating a malfunction in a machine. Noise, a possible source of annoyance and discomfort to personnel, and over a long time, even a possible cause of deafness. For some years now, the Navy has been developing methods to combat and cope with the problems of shipboard noise. This work involved the use of some highly specialized equipment. In this film, you will see basic procedures for calibrating and using various types of this gear. Your own ship or facility may have different types than we'll be using here, but the underlying techniques are all the same. There are several different kinds of surveys. Here are the ones we'll talk about in this film. Airborne noise surveys measure noise carried through the air that can interfere with speech, cause annoyance, and create hearing problems. There are two categories. The first deals with total airborne noise, including the racket from various shipboard machines. The other deals exclusively with that inevitable wheeze from ventilation and air conditioning systems. Next, we'll take up structure-borne noise, or vibration surveys. They provide a direct measure of the sound produced by individual machines. The basic structure-borne survey provides broadband data, the so-called Chapman numbers. A more elaborate survey provides third octave data, which gives a far more detailed picture of the noise. Our first topic, the total airborne noise survey. This type of measurement is taken at the completion of an overhaul period and may be done at other times when needed. The job is normally handled by shipyard personnel, but may also be done by ship's force. Before starting any survey, you must check and calibrate your equipment. An airborne survey requires two basic items: a sound level meter and an octave band analyzer. In some equipments, the two are combined. The sound level meter picks up the noise from the air and gives a direct reading of broadband dB level. The analyzer enables you to examine the noise more closely by measuring the level in a number of frequency bands. The first step is to calibrate the sound level meter. This type, a General Radio 1551C, is turned on by raising the microphone to the upright operating position. Check the batteries by switching to each battery position and ensuring that the meter reads in the proper area. Then leave the switch in the meter slow setting. Now set up for calibrating. Put the waiting switch to cal and do the same with the attenuator switch. The meter should now read in the cal area. If it doesn't, adjust the thumb set control. So much for the internal calibration. The next procedure checks on the accuracy of the meter readings. You'll need an audio oscillator, a voltmeter, and a device called a calibrator, which feeds the audio signal into the microphone. One instrument available for this job combines all these items into a single unit. The calibrator is labeled to show the frequency and voltage it's designed for. In this case, 400 hertz at 2.0 volts. The unit hertz, of course, is what used to be called cycles. Connect the calibrator to the 600 ohm output terminals of the oscillator. Connect the VTVM to measure the oscillator output and adjust for the specified frequency and voltage. For accurate results, you've got to be sure the voltage is exactly as called for. On the sound level meter, the weighting switch has been set to 20 kc and the attenuator switch to 120. Put the calibrator firmly on top of the mic to feed in the signal and read the meter. It should be within 1 dB of 0. If not, adjust with a thumbset control. The sound level meter is now ready. Next, the analyzer. Check the batteries and leave the meter in slow. These steps are standard for all sound measuring equipment. Set the frequency band selector to all pass. The analyzer should now give the same reading as the sound level meter. With the attenuator at 120 dB, the pointer should be at 0. If not, use the thumbset adjust. That completes the calibration. The only other maintenance required is to check the internal noise of each instrument. Details of this procedure are given in the manufacturer's handbooks. Now you're ready to conduct the total airborne noise survey. Measurements are taken in port using the sound level meter and analyzer. The point is to determine how much noise the crew will hear in each compartment normally occupied as a living or working space. If any compartment is too noisy for comfort or health, corrective measures will be taken. Readings are taken with the weighting switch on 20 kc. Shut down all compartment machinery except those that the ship has ordered be left running. Then take an ambient reading, a measure of the background noise. Hold the sound level meter where personnel in the compartment would usually be and at their normal ear level. The reading is always obtained as the sum of the attenuator setting plus the meter indication. In this case, 70 plus 5, or 75 dB. That's broadband, the total background noise level. A more detailed picture is provided by the analyzer. Take dB readings in the same manner for each frequency range. When you've got all the background readings, you're ready to take measurements of the compartment noise. To the extent possible, all machines in the compartment should be operated as they are for normal underway steaming. Take the same readings over again, broadband, from the sound level meter, and octave bands from the analyzer. Remember that the reading is the sum of attenuator setting and meter indication. This data will later be corrected to account for the effective background noise levels, yielding absolute values of the airborne noise in the compartment. For ventilation system noise surveys, the same type of equipment can be used. As you've seen, preparing the gear involves calibrating the sound level meter and then making sure the analyzer gives an identical reading. Aboard ship, you again start with background noise levels. But this time, you're interested in the noise caused by the ventilation or air conditioning system. Turn the system on at high speed. Then take the data readings to determine the maximum noise level from this source. Next on our list are the structure-borne noise surveys. Broadband surveys are required to be done by ship's force once every month. For demonstration purposes, these surveys are taken in a training facility. The sound level meter you use must be provided with an extra attachment, an integrating control box, which contains some additional circuitry. An accelerometer is used instead of a microphone. To provide a single frequency calibration of the system, use this self-contained vibration calibrator. The accelerometer has been attached to one of the side discs with double-sided masking tape. Connect the pickup to the integrating box and set the selector to acceleration. When the calibrator is turned on, the side disc vibrates in a controlled, precise way. Adjust the level control for a meter reading of 135. The sound level meter should now be indicating an exact amount as specified in the handbook for the particular combination of equipment you're using. Calibration at many frequencies can be provided by this type called a calibration exciter, which requires some auxiliary equipment. On most ships, mounting blocks or washers, such as here, have been attached to each machinery unit for use in the structure-borne noise survey. Be sure the washer is clean. Then apply a thin coat of silicone grease. The accelerometer is attached to a magnet and is placed on the washer. To the extent possible, shut down all machines in the compartment, including the one to be tested. Then take a background vibration reading. Turn on the machine being tested and note the new reading. It should have increased by at least 10 dB. That's your assurance that background noise will not obscure the data. So go ahead with taking your measurements. You take 3 readings on each machine: acceleration, velocity, and displacement. Broadband structure-borne noise surveys provide a check on whether any machines have become excessively noisy. 1/3 octave surveys do the same thing in a more thorough way by measuring the noise in each narrow band of frequencies. In addition to the sound level meter, the 3rd octave measurements require an analyzer and a graphic level recorder. What does each of these units do? If you followed so far, you should know most of the answer. The accelerometer converts the mechanical vibration of a machine to an electrical signal. Depending on setting of the switch, the integrator alters the signal to provide a measure of acceleration, velocity, or displacement of the machine vibration. The dB levels of these 3 values are read from the sound level meter. These are broadband measurements. Next, the acceleration signal undergoes a narrowband analysis. In effect, the analyzer divides the signal in narrow frequency bands. You then measure the dB level of noise in each band separately. The narrowband data is written out on a paper sheet in the form of a graph by the graphic level recorder. Here's how you prepare this system for use. After you've calibrated the sound level meter, connect it to the analyzer. And connect the analyzer to the graphic level recorder. Now, calibrate the analyzer so its reading matches the reading of the sound level meter. To do this, set the analyzer to measure broadband noise by putting the selector switch on all pass. On this type of instrument, there are two controls for meter range. Set the inner dial and the outer one to provide an on-scale meter reading. The vibrator is on, and the sound level meter has been adjusted to give the prescribed reading for the type of pickup in use. In this case, it's an attenuator setting of 90 and a meter reading of 1.7. Adjust the analyzer to give the same meter reading, 1.7. Now, here's an important item that often leads to confusion. You have just calibrated the analyzer to match the reading of the sound level meter, 91.7 dB. But the 90 part of that figure does not show on the analyzer dials. You must remember throughout the data taking that the outer dial of the analyzer corresponds to 90 dB. We'll review that in a moment to be sure you've got it. The next step is to calibrate the graphic level recorder. In operation, the paper comes out like this, and the pen moves up and down to record the dB levels. The baseline of the chart can be made to represent any convenient dB value. We'll assign it a value of 60 dB. Now remember that we're still feeding in a signal of 91.7 dB. The entire system is now calibrated and ready for use. The newest addition to this system is a dial drive unit that will synchronize the analyzer and the graphic level recorder and takes the place of the old chain drive. The third octave survey is required every 6 months and can be done in port or underway. You begin by taking broadband data from a sound level meter and recording it on the cards. This is the same as the monthly broadband survey. Then switch the integrator to acceleration for taking the third octave data. On the strip chart, write down all the identifying data and make a short trace of the broadband noise. Set the analyzer to the third octave position and tune to a frequency of 10 Hertz for the first reading. Record a short trace and put down the frequency. On this type of instrument, the points at which you take readings are shown by the white dots on the frequency dial. These are the center points of each 1/3 octave band. But what happens in the case of an off-scale reading? If you remember what we said earlier about attenuator settings with this combination of equipment, you'll know the solution is to adjust the dials on the analyzer. Turn till you get an on-scale reading. You have changed the level of the signal being fed to the recorder by 40 dB. Be sure to write this change on the chart. You must remember to write down every change in attenuator setting, or your data will be worthless. Third octave data is collected from each machine through the entire frequency spectrum, from 10 to 10,000 hertz. In this film, you've seen the basic techniques for handling some of the equipment commonly used in airborne and structure-borne noise measurement surveys. The accuracy of the surveys you conduct will be no better than your understanding of the theory, the equipment, and the methods of noise measurement. Before you begin, and whenever you're in doubt, consult the handbooks. They are, as always, your best guide to accurate and reliable work.